as that is there.
We're saving our food when you're doing the presentation, so we can. He said he gets.
Get over it. Oh, so it's not. I think you go by now. the plan is to meet somewhere in front of the building the day of. Speaker, this is Erfan at the Western Cooling Efficiency Center, who will be presenting on advanced heat applications.
Hey, good afternoon, everyone. So I'm kind of less than a year joined to the Western Cooling Efficiency Center, but before I was a postdoc working with Vinod Narayanan in Mechanical Engineering Department for 2.5 years. So, but this last year, after joining the center, we had some ongoing projects, but we kind of used some of the experience that we had with the previous projects and then to come up with the new projects that is very relevant to the projects that we have in the cooling center related to the cooling and heatings of the buildings. So this project is explaining the steps that we have done so far and also the future steps that we are going to have. So in these recent years, there has been a transition for these to the new refrigerants from the conventional refrigerants like R410A. So these refrigerants have low global warming potentials, also, but they do have some risk like a flammability and toxicity. So they are recommended to be sealed and packed in a unit sitting in the outdoor. So that brings a need for a secondary loop here that whatever cooling or heating load that we have on the outside, transfer it to the inside, to the indoor, and then we exchange that heat with the and condition the air inside the buildings. So that means that this package as a heat pump sits here, and then our intermediate loop, which can be with a glycol solution or water solution, that takes the heat or the cooling load and brings it inside, and in the attic or closet inside the buildings, we do have a second heat exchangers. So usually they call it air handler, to exchange that heating or cooling load with the air, and that air goes inside the rooms. So there are some characteristics of these two heat exchangers. So the first one, which is here, so we have an evaporation of the refrigerants on one side, and also let's call it the second transfer fluid is the water. So water is always in the single phase. But in the second heat exchangers, there is no phase change of the fluids here. Water stays water, it's just a sensible heat, which is transferred from water to the air. So this brings some limitation and some potentials. Here is that, so whatever temperature that the water reaches at this point, let's say 40 Fahrenheit or 45 Fahrenheit, when it reaches to inside the building, there is going to be some heat losses here. So maybe we'll lose few degrees here or gain a few degrees. But on the other side is that we are not bringing a high pressure fluid all the way inside the buildings. So that means that our air handler might be smaller, not rated for the high pressures, so that makes it a lighter and maybe cheaper air handler units for us. So these two types of the heat exchangers we showed here, so the classification of this heat exchanger is based on the direction of the flow. So either in the worst case scenario is that you bring the fluids, we are going to have two fluids here. If the fluids goes in the same directions, that's a worst case. But in the best scenario is that you bring the fluid in the counter directions to exchange the flow. But based on the manufacturability constraints here, there is another configuration which they have been used for this air handler, and which is called cross flow. It's less efficient compared to the counter flow, but it's easier to be built. So for this heat exchanger, which we have a phase change, and here's single phase, this configuration, let's see that what's the effect on the efficiency of that air handler unit. On the top, we have a plot for the effectiveness, which is 1 means that the ideal case, that means that if you bring the cold flow for example, 40 Fahrenheit, the hot flow that comes in, if we have an effectiveness of 1, that hot flow should be cooled down all the way down to that 40 Fahrenheit. But that never happens. But again, for these effectiveness of one, we have a curve here that compares the cross-flow configuration with the counter-flow configuration for the case that we have a phase change. You see that these two curves are aligned on each other. That means that there is no dependency on the configuration of the flow direction when we have a phase change. But when we are dealing with the single phase flows, like water on one side and air on the other side, these two curves are differing from each other. That means that for the certain number of transfer units, which is a unit for characterizing of the heat exchangers, for the same NTU value, you have different epsilon or effectiveness for your heat exchangers. That means that if you have a counterflow, you definitely have a higher effectiveness, even more than 10% increase in your efficiency. So on the left, we have pictures of showing how these conventional air handler units or heat exchangers for transferring between water and air are built. So they are essentially tubes that are bent in the shape of a coil that brings several passes of the tube when the flow of the air passes across them. And there is a fan that blows or sucks the air through these tubes. If we have more layers of these tubes, we have more heat load or capacity of this heat exchanger, but there is a higher pressure drop in the air handler. And these fin structures you see on the outside is to increase the heat transfer surface area of the air handler units, and they have been built in different shapes, in different spacings. The closer they are, the higher pressure drop is. But different shapes brings a little enhancement in the heat transfer. But let's put this aside and then let's have a flashback to the previous projects that we had when I was a postdoc. There was a project for this heat recovery, and that was essentially like if you have a turbine or generator, whatever, at the part of the system, they are dumping a huge amount of the hot air into the atmosphere. So this project was focusing to see that how we can harvest that amount of the heat into the loop that works with the supercritical carbon dioxide and use that cycle to either generate the heat or do other applications. So that the limitation that we had, it was that we shouldn't propose too much of the pressure drop at the exhaust because that drops the efficiency of the turbine or generator. And so that's about the same thing that we have in the air handler unit. You can't have these fins very close to each other because you have a certain inch of the water that you can't go beyond that for the pressure drop of the air. So the same kind of a limitation here, but the pressure of the supercritical carbon dioxide was much higher, about 3000 psi, and the temperature that we were dealing was about 500 degrees C. So definitely we were working on some kind of a super alloy heat exchangers. We were collaborating with the Carnegie Mellon University, and we were developing the model, and they were building the heat exchanger like these shapes that you see here, and using the additively manufacturing process, essentially putting layers of the powder and using a laser to go and melt those sections that you have, and at the end drain those trapped powder, and we have a part here. And so we got those steps of the designing, modeling, and then getting the heat exchangers fabricated and bring it here in UC Davis and characterize them. So through all of these projects, we ended up to have a model, a correlation-based model for designing this type of the heat exchangers, where we need to have a low pressure drop on the gas side. So we also, in the performance characterization, we showed that we can have effectiveness of much higher than above 80% in our design. So we got this model for this microchannel heat exchanger design and used that model for this application, for HVAC applications. So over there we were dealing with the Inconel alloys, but here we wanted to have something much cheaper, cost-effective, and also maybe something that can be built much easier. So we ended up to choosing plastic properties for the heat exchanger. So we tweaked our model and changed the conductivity of the material to those available plastic information that we have. And then we try to compare this with those conventional fin tube coils that are out there. So we have a model for this one and a model for this conceptual design for the plastic heat exchanger. And then here, as I said, if you add the number of the passes of the tubes, you are increasing the pressure drop. Here in this concept design, we have cooling plates or heating plates that the fluid, the second fluid, like a water, goes inside each of these plates and get distributed by this headering here. And between these plates, there is a spacing that the gas or air is passing through it. And inside of each of these plates, there is a micron size, maybe 500 micron gap, and there are some microstructure features inside. So if you, in this plot, what I'm showing comparison of the effectiveness of these two concepts with the pressure drop. That means that by keep adding the rows here, you are increasing the pressure drop for this fin tube case. And here, by making these plates closer to each other, you are adding the pressure drop on the air side again. So here you see that for the same kind of a pressure drop of the air side, for example, 50 Pascal, you are reaching, for the effectiveness-wise, the green line shows the microchannel plastic heat exchanger, which we are about 10-15% higher effectiveness for the plastic one. And also for the heat load, again on the right side, you see that you can have about 13, close to the 14 kilowatt of the heat, more than 3 ton of the cooling, and for the same parameters in terms of the water flow rate, air flow rate, you get less heat load through these coils. So you may say that, hey, if you go with the plastic, so these coils are made with the copper, that's a much conductive material here. So why in your design you have a plastic which much less conductivity here? So why is better than the other one? So the thing is that, so if you just say that we have a hot air here and a cold water here, and the direction of the heat flow is this way. So you have 3 different resistances here. One is for the convection, which is happening on the air side, conduction through the plastic and the material that you have, and again convection on the water side. For this case of the 50 Pascal, these are the resistance values on this model here. That shows that you see that the resistance of the conduction and the convections are about the same order, but the resistance of the on the hot side, the air side, which is always the bottleneck for us, it's more than 10 times here. And this is mostly because in our design, in microchannels, we are dealing with the very small and thin valves here. For our case, it's about 500 micron, half a millimeter. So when you have a thinner valve, that definitely doesn't impose too much of the resistance to your heat conduction. So we have some promising results here, in at least calculation-wise. Using that model for the microchannel heat exchangers, there was another study here in Cooling Center by Curtis, Derek, and Rachel, that they were studying a house here in UC Davis, which was instrumented, and they collected the cooling data of this house for between July to August of 2018, which ended up to about 540 hours of the cooling, which is the residents of that apartment or building they used. And we said that, okay, the project that they were dealing is that instead of using the heat pump, they used a sub-wet bulb evaporative cooler using a system that just boils off the water and use that evaporative water to cool down the the water which is on the basin on the bottom, and then use that water, send it inside the air handler, and chill the air inside the building. So if they were using these fin tube model, fin tube heat exchangers, the model that they had in this coupled model here, they ended up to the chart here, which shows number of the hours which the load that the residents needed, but this approach was not successful to was not sufficient to provide that amount of the cooling. That showed that from these 539 hours, only 140 hours, this system coupled with this fin tube was not successful to provide cooling. But we said that, okay, instead of this guy, let's go with the microchannel heat exchanger to see that how much of that kind of unmet hours would be. And then this showed us that we can reduce that hour to less than a third, 45 hours, if we use this plastic heat exchanger in the same kind of conditions, in the same flow rate, which was about 1200 CFM and 5 gallon per minute of the chilled water which was coming into the air handler. So this is again another example that these microchannel heat exchangers have some possibilities that if we push them forward. So we wanted to make a prototype here and say that, hey, we do have a model, it shows some calculations, but is it really going to happen if we build one here? So we wanted to make one and test it and see that we show that our model is validated for the metal heat exchangers, but how about these plastic ones? So
did you size the heat exchanger for 50 pascal?
yes, that thing was about the same. Let me go back.
The sizing would matter.
So the sizing that we have, the same sizing was about 2 feet by 3 feet. The same cross area that you see here, the same thing here.
Cross-sectional area. So was there also a reduction in pressure drop for the fan?
I don't have that number here, but the pressure drop, we had that criteria of the 50 Pascal that you told to we know, so we wanted to keep it like that. So spacing of these plates together, we put them sparse in which that we don't go beyond that number.
Okay, but you're limited by your cross-sectional area.
Yeah, the size of the heat exchanger is like that. So there is a team lab in the Genome and Biomedical Science building, and which we have been working with them to make some prototypes for our designs with them. So recently they got this fancy machine, carbon 3D printer. So this machine has a resin bath on the bottom, and the probe which goes inside these resins, and this machine takes the CAD model and projected from the bottom this CAD model to inside these resins, and using a UV light cures layer by layer of these resins, and gradually this probe is sticking out, and you see that the solid part is sticking to this part here, and then you detach it from here. So that's the application. They call it continuous liquid interface production, or clip 3D printing. So this machine gives very fine and smooth surfaces, and they can use different kind of resins with different properties. So this is the model that we have for that metallic heat exchanger, which actually I brought one of the examples here we can pass around. That's an Inconel alloy. So using the same model, not changing anything, just half section. We wanted to see that this machine is successful to make that. So we went first, we didn't know that it can go with those wall thicknesses that we have, which we were thinking about 500 micron or less. So we made one model with a 1 millimeter wall thickness everywhere, and then the other one, and this was successful. We pushed it down to the 500 micron, and again this machine was able to make these geometry while the internal channels was open. So we moved forward and to make a full design. So based on that correlation-based model that we had, we in order to have an effectiveness of more than 90%, we chose the parameters in terms of the lengths, widths, opening, and the spacing of these plates from each other, and we ended up to having a design like that. There were lots of consideration here based on the direction that they are building or they are pulling out of the resins, in terms of that you can't have the overhanging geometries, so everything should be in contoured shape somehow that it can be supported, especially for the internal geometries, that there is no way that they can put some support structures. So this is the shape that we made it. We came up. So it's about a foot long, 2-inch wide, and a 4-inch width here. So this shows a section cut here. There are 33 of the water plates here. That plenum distributes the inlet water to 33 of these plates, which that cross section here shows what is inside that plate. There are micro pin fins inside with a height of the 0.5 millimeter, 500 micron, and their spacing came out of this model here. So these plenums takes the water and distributes into each plate, and once, for example, you have the air, hot air comes from the top toward the bottom, and you bring the water, chilled water from here, so toward the top. So you have kind of like a pure counterflow design in your heat exchanger. This shows top view of the design. This shows a close-up view here. And you see some features here because we wanted to put some structures inside that this plenum can withstand the internal pressure. Next slide I'm showing as a part of the process to design that heat exchanger. We want definitely have the structural integrity of the design and also the uniform flow distribution. So we had these steps that take one of the single unit here, whatever pressure that you want to impose to the internal wall, and see that how you have the stress distribution in your features, internal features. If it's not rated for that pressure, you have to add more of these pin structures here and bring them closer. The criteria that we had, it was about 10 bar of the internal pressure, and then we designed our plates based on that. On the plenum section here, again, the uniformity of the flow was essential. So we ran some fluent model on this plenum here, and you see some pictures here that shows that when the fluid comes here at the end, when there are some openings here, and each line here feeds one of those 33 plates here. This is the velocity magnitude contours. And here this plot again shows the velocity magnitude versus the position. If you take one line from here all the way to that, that shows the value of those velocities, which is almost close to uniform distribution. So there were 4 or 5 steps of the redesigning of this plenum section until that we could have this kind of design here. So I showed the full design to you, but again, we were not 100% sure that they can make it. So we made some smaller section of that full model, or we call it subscale heat exchanger, and then gave them to print them to see that if they can successfully, based on the direction of the pulling out of the resin, can they make it? And these are some of the pictures of the part that they made. On the other efforts, we wanted to make this wall even thinner than the 0.5 millimeter, 500 micron. We tried 250 micron, 400 micron, but we ended up to have some of these walls very, very not support somehow that they burst easily. So we stick to our 500 micron wall thickness. Kind of I can say that the printer couldn't go less than 500 micron in order to make a thin wall, a good thin wall. So after having all of these parts, we moved forward to make a full design. So definitely the first thing that we were not expecting, but that happened. This was not successful build of the whole design. So they ran the printer at night, kind of in the afternoon, and they were expecting that based on the build time, it will be done in the next day morning, the following day morning. But when they came, just 1 hour before the end, they ran out of the resin inside the bath. The cassette was dry, so this just very, very bottom section was not built, so it was just all open. But part of this procedure is once that the part is done, you have to run the IP alcohol through the model for about 30 minutes to make sure that those internal channels are drained fully from the resins. So the first one was not good. So for the second one, they started in early morning, and then before they're going back home, they just again add top of the resin with more of top of the cassette with more resin. And this is how the second heat exchanger came up. And so it's fully made. The air side, the channel side, everything is perfect, it's smooth, it's open for the air side. One thing that we noticed, we do have a little high pressure drop for the water side. That kind of shows that it seems there is some trapped resins inside each of these plates that they were not fully drained. So we are working with the parallel passes here. One, using this design, since it still is working, we want to make a loop and characterize it thermally and also the pressure drop side. And also change this model a little and again make another one to make sure that all of the internal channels are fully open. So in the Banner Hall, Professor Vinod Narayanan, he has a lab over there, and we are using that facility here to put together this loop and hook up our heat exchanger here. We are measuring the pressure drop of the air side, the inlet temperature, both air side and also the water side. We are sending, using the chiller over there, we are sending a very cold temperature water inside, and we run the building air inside at room temperature to see that how cold we can have the air at the exit. But if everything goes well, and then we move forward and also try to preheat the air to the certain temperature, 80 Fahrenheit, 85 Fahrenheit, and characterize in more temperatures. That's pretty much what we have now. Was good?
How it gets into the market?
So right now, this model, since was made using this approach, this technique, it's like a proof of concept, which show that, hey, the plastic heat exchangers can be built and the performance is based on our predictions. We can use our model kind of to tweak a little more design and also go to the way that they can be made, not just by the 3D printing, maybe with the extrusion of the plastic. So be in more industrial form rather than the lab case. And if we go, there's two approaches here. We can go with a smaller scale and use the modularity to kind of hook up more of these units together in order to reach to the certain load that, for example, a bigger house needs rather than a room. Or just go with the full and bigger model made by not just the 3D printing, maybe extrusion, and then that also can be applicable for those buildings. But for the first shot, I guess the residential buildings, for local cooling, these are the applications we are looking for. And in terms of the customer, we have to look into that. If the proof of concept is done, then we can. Not yet. The loop is just hooked up, and then maybe in the next week we'll start collecting our data. So it hasn't been done yet.
The optimal point where after that offsets the
This is based on so in the air handler unit, if they have a fan, and depending how much of these ducting are going to reach to the rooms, so that dictates how big is the fan, and it's just a rule of thumb, I guess it's safe if we keep it in the 50, but even that emergent coil picture that I showed up there, that the pressure drop just at the core is around 100 Pascal itself. So it's something to see that how available pressure drop you can have in your home. I guess forget. I use this for recording or something like that.
The recording is a little bit better.
I'd like to introduce our second speaker here, Ryan Barr. Very exciting.
All right. So I'm Ryan Barr. I'm a PhD student in the energy graduate group here. Why it might not be advancing.
Screen or it's full screen, I guess.
Of course. Yes, I have one of those.
Computer, but not.
All right. Okay. All right, so I'm going to run through some slides I used recently to give a very high-level overview and pitch for our startup company, Repurpose Energy. And what we do essentially is reuse electric vehicle batteries to store solar energy in low-cost stationary energy storage systems. So I'm a PhD student in the energy graduate group here and a co-founder of this startup. So for general audiences, I generally start with the fundamental problem that is motivating our work, which is that even our own federal government came out with a report late last year saying that climate change is here and it's expensive and it's deadly. So the International Authority on Climate Change said that we need to produce a majority of our electricity from renewable sources by 2030 and almost all of it by 2050 to keep global warming below 1.5 degrees C. So I like to ask, who thinks the United States will accomplish these goals? About 5% maybe. How about California? Okay. I share your optimism, and I have a little bit more, I think, because solar and wind are the cheapest ways to generate electricity, and many states, including California, are ahead of schedule to meet these goals. As many of you probably know, we have so much solar in California now that there is an imminent need to store that excess solar energy produced during the afternoon for use at night. So getting into the more specific problems that motivate our business, electricity, essentially, to grossly oversimplify, used to be most valuable in the afternoons when the sun was out, and consumers could save a lot of money by installing solar, and there wasn't much need for energy storage. But now we have so much solar that peak electricity rates are essentially in the evening when the sun is setting and when the sun is down. And this is a problem for solar companies because it, again, to simplify, essentially cuts savings from solar in half, but doubles potential savings from energy storage. So large stationary batteries at buildings, especially commercial and industrial buildings, because they have large demand charges, which we can talk more about. These large stationary batteries are now great investments. These payback periods are typical, given investment tax credits, accelerated depreciation, incentives like SGIP, and the declining cost of batteries. So the bottom line is that solar developers essentially need to pair their solar panels with energy storage to stay in business. So this explains explosive growth projections in the market for stationary energy storage in the US. It's about a $1 billion industry today and will be about $5 billion by 2024. But this growth pales in comparison to the ongoing growth in electric vehicle battery demand. You can see here that this is from Bloomberg New Energy Finance. Growth in electric vehicle battery demand makes growth for stationary batteries look almost flat. And 95% of these lithium-ion batteries have been landfilled historically because recycling them is uneconomically expensive. In other words, the cost of recycling lithium-ion batteries is about 3 times the value of the recoverable materials that you can get from the recycling process. So this is a problem for automakers because legislation is coming in California to put automakers on the hook essentially to reuse or recycle all their batteries. So recycling is expensive, but reuse is a great option, given that 75% or more of battery capacity is typically still there at the end of a battery's useful life in a vehicle. Any questions so far? I want to encourage questions throughout because, number one, I want to use this as an opportunity to get your feedback and thoughts.
When I was doing, it was a while ago, when I was doing a literature review on storage, I came across this article that the federal government is actually using not basically Tesla, but Toyota Prius's batteries as a substation battery backup or something like that. So they're storing the energy in the batteries and then they're using it. So what is different about this and that you basically want to provide the storage for everyone?
So, yeah, our idea is essentially the same. We think the timing is right and we have the right technology and the right team, and we're focused on a specific market, which is commercial and industrial end users in California. They can save the most from energy storage, and the supply of used electric vehicle batteries is here in California. So it's a well-recognized idea, and we're just trying to execute on it because not a lot of companies, no companies, in fact, are profitably doing it right now.
Last, or just doing a small scale of doing an experiment?
Yeah, there are a lot of experiments. Car makers essentially are doing a lot of pilots to use second life EV batteries for backup at their offices. There's some research going on in San Diego. UC San Diego researchers partnered with EVgo to put second life EV batteries at fast EV chargers to reduce EV chargers' demand charges or electricity bills. So it's an ongoing research area, definitely. Yeah.
Would this model meet the California requirement of recycling the battery?
So the legislation that's coming is to ensure that as close as possible to 100% of these car batteries are reused or recycled.
So reuse is an option.
Right.
On that.
Right.
Storage, and then you're still going to have all these batteries.
Right.
So is that, are they planning to address that?
It's a good question whether or not after reusing electric vehicle batteries, then do you need to recycle? We plan to recycle because we're committed to, environmental benefit. It's unclear, what the legislation will be because that process is still ongoing and we're involved in it. Yep.
Are you going to get into the technical specs
Not too much today, largely because we're not exactly sure what the specs of our initial product will be. I'll say we have a commercial scale demonstration, which I can tell you more about. We do plan to limit the state of charge a little bit just to preserve the lifetime of the battery, but we're not exactly sure what for example, the power and energy capacity of our initial product will be. We do know that the fundamental building block of all our systems, which is this 2 kilowatt hour sort of module, which you could fit in your hands, or in your arms anyway, it's like 50 pounds or so. It's modular, so it's highly scalable, and we can scale up or down the power and energy capacity based on the customer's needs. A little bit, yeah. Okay, just to digress a little bit also on this point, we're currently getting our used batteries from Nissan. We think they're a great candidate for an initial supplier because the Nissan Leaf was the best-selling car between about 2010 and 2016 in this area, and just the Leaf sold in California during that time period could provide our first few $100 million in sales potentially. But the batteries we get from them, what they have right now, are batteries that drivers take to dealerships to have replaced. So they're inherently not the healthiest cells, and we're exploring other ways to get either cheaper or healthier batteries. For example, a lot of cars end up at dealerships and they don't resell immediately, so they're sold at auction to scrappers or whoever else. So if you have any good ideas on how we could get cheaper or healthier batteries, I'd love to hear those because we're sort of trying to look ahead at our next supplier. Okay. So again, our joint solution to these two problems, which is electric vehicle battery waste and the need for cheap energy storage, is to reuse EV batteries to store solar energy. And our value proposition is that we're looking to sell energy storage to commercial solar developers, specifically in California initially, at less than half the cost of new battery alternatives. The trade-off is that these things take up more space because they are partially degraded in their old technology, and they also don't last quite as long as new batteries. But finding that capital cost is such a barrier to the deployment of energy storage that people really value the cost advantage of second life EV batteries. So the most expensive consulting company in the world just a few days ago issued this report, which sort of, I think, speaks to the timing of this idea. The supply of EV batteries is finally there, the demand for energy storage is there, and mainstream capital is starting to acknowledge the value here of second life EV batteries. So this is general, but in a nutshell, our technology allows us to reuse these batteries safely and efficiently for, we think, about 7 years. After that 7 years, we will just refresh the cells that are too degraded to merit continued use. So we'll recycle those and we'll replace them with new used EV batteries. So specifically, our core strengths are really battery testing. So we can do this quickly and accurately. We use algorithms to test these batteries, individual cells, without needing to fully charge and discharge them, which speeds up the reassembly process. We've also learned to use, for example, inverters to do the battery testing instead of these really expensive testing stations. And so the speed and accuracy of battery testing is really essential to the profitability of this venture. Yeah.
So when you get to the end of the lifetime of these first set of used batteries, what happens if you do switch to like the original container with all these batteries and you switch to ship both batteries and they come in different spec? Is it an issue if you're mixing and matching batteries?
So the battery management system, which is sort of the brains of the operations, it measures the temperature and current and voltage and estimates state of charge and communicates with the inverter and all of that. That battery management system will be flexible, so it could allow for that. I think the biggest challenge will be the mechanical engineering. You know, if we have this space allotted for these flat pancake-shaped Nissan Leaf modules, and we have to replace it with something that's a different shape, we might run into challenges there. And so we will anticipate those as we design our systems, but it's a good question and definitely a challenge. Interoperability of different battery types. I mean the upfront capital cost. It's a good question. These total cost of ownership analyses are much more nuanced and much more complicated. You know, it depends on a lot of assumptions and the end user's demand profile and rate structure changes in the future and all these really complicated things. The cost advantage is less than 50% because our batteries don't last as long, like I said. So it's hard to generalize. But the cost advantage is still there, we think, in many cases, given our assumptions, but it's less than half. Yes. Yeah. So another key strength for us is the battery management system. So we have an exclusive licensing agreement with an electric bus manufacturer. So we have access to their technology, their battery management system, their engineers, and we've started to adapt that technology for these stationary second life systems. That battery management system is especially key when you have used batteries that have variable states of health and internal resistances and so on. So that technology is key for us. This efficiency, I mean the charge and discharge efficiency of the battery itself. Most of the losses in these systems actually occur when you're inverting, DC to AC current. So that's what I mean by 97%. And that is right up there with the charge and discharge efficiency of new batteries, which is maybe 98 or 99%. So there's not a significant efficiency loss by reusing EV batteries. So I am the least technically capable person on the team, even though I'm an engineer by training. I'm really focused on communicating with potential partners and customers and investors. Professor Jaewon Park has been doing this research here for about 9 years with the California Energy Commission and PG&E and U.S. Naval Office of Research. Joe has been helping him out as a student in his lab for about 3 years. He was instrumental in the development of the commercial scale demonstration project we have, which I'll tell you more about. Sean spent years in the Navy as a weapons system engineer, so don't mess with him. And then we have advisors who have a lot of experience with fundraising because that's sort of a gap in our existing team. So Peter, chair of the Clean Tech Committee of the Kairetsu Forum, which is a global network of just venture capitalists and angel investors generally. And he's been a CFO in the space for many years. And others, countless others. Ben, for example, deserves to be on this slide. He's been really instrumental. He deserves to be on the payroll, in fact, so we won't forget that. And then Meg is joining our team this summer during this NSF program, which I'll tell you more about as well. So,
Question from Gil.
yes, Gil.
I have two questions.
Yeah.
So the first one is you talked about combining these two business cases.
What was the last part?
How do I start my startup here?
Okay. So let's see. First question, have we considered using new batteries in the interim and then perhaps use batteries later on? And yes, we've considered that. In fact, we've been meeting a lot lately with a longtime solar developer who's developed their own energy management system, which is sort of the higher level controller that directs the battery to charge and discharge, basically sets that scheduling to optimize savings for the end user. So he has this controller. He wants to go to market right now, so he wants our help basically selling his new battery product today, and we're wrestling with that decision a little bit. Our sustainable competitive advantage is the ability to reuse electric vehicle batteries. We think that's really going to pay out in the long term, just given the supply that's about to be dumped on the market, these legislative requirements to reuse or recycle, and many other factors. So we want to stay focused on the long-term vision, but it is tempting to use new batteries in the short term, especially because our used batteries don't qualify for SCHIP. And so that's a major barrier to selling our systems in the short term. We think it's likely that as the rules are rewritten for SCHIP, we get that exclusion removed. But that's a long-winded response to that first question. The second question, there are lots of resources on campus for professors and students who want to commercialize academic research and technology and build businesses out of them. We can have a more extended conversation about like competitions and organizations on campus that exist for that sole purpose of technology commercialization. But the university encourages it because I think that the ultimate goal is to bring these ideas out into the world, right? And to do that, generally, you have to build a profitable business case around them. So we're going after grant money and private investor money and every other source of money and support that we can go after right now. So lots of resources. So this is a schematic. Yes?
What's SCHIP?
SCHIP, sorry, good question. So it's basically the rebate program for these stationary energy storage systems in California. Generally speaking, when you pair a battery system with solar, you can get a 30% tax credit on it. So that basically knocks down the cost of the battery system by 30%. And then this rebate program knocks down the cost of the energy storage system by another 20 or 30%. So, the government is essentially subsidizing a huge percentage of the cost of these battery systems.
If you already have solar, do you still get the 30% tax credit on added storage?
So the IRS is a little fuzzy on this. It looks like for residential, yes, you can retrofit as long as you can demonstrate that the battery is only charging from solar. Same goes for commercial and industrial. It's actually a little more lenient even for commercial and industrial. So the bottom line is yes, you can retrofit an existing solar system with energy storage and get that tax credit as long as you're only charging from solar, basically.
The solar tax credit is going away. You guys thought about the business plan, financial structure?
Yeah, so it starts to step down next year, goes from 30 to 26%, and then continues to decline from there. Cost pressure is only going to mount, when that tax credit starts to go away. So, we'll be on level footing with all the other energy storage providers out there, and that step down is factored into these estimates of growth, definitely. And so the opportunity will exist for us and others, mainly because rate structures continue to encourage energy storage. Wholesale market participation continues to get easier. So there are all kinds of other ways you can monetize these energy storage systems that are, emerging and expanding over time. So this system was paid for by a California Energy Commission EPIC grant that the team won in 2015, long before I got involved. And essentially, the team reassembled the equivalent of 15 Nissan Leafs, Nissan Leaf battery packs in the shipping container at the Robert Mondavi Institute here in Davis. And we used those batteries, or charged them from excess solar energy from the rooftop array there during the day. And then we discharge the batteries at night when electricity is generally dirtier and more expensive to reduce the evening energy demands of the facility by about 20%. Next step is to build a similar system, essentially at a local business, to profitably reduce their electricity bills and carbon footprint. And this will be made possible by a grant we won from the NSF recently to essentially go and interview a bunch of potential customers and partners this summer. I'll be doing that with Meg starting in July. And it'll also be made possible by cash prize from the Big Ideas competition, which Camille mentioned. Over 330 teams applied to that, and we won first place in energy and first place overall. So that was huge for our team. The money is nice, but more than anything, the validation and the connection to investors and things like that have been really helpful already. We have a couple other, things in the works. We have the Big Bang competition still going on. We're one of the last 15 teams in that, which will wrap up this month. And then we think we'll get good news from CalSeed to demonstrate a non-destructive fire suppression system. We'll hear back on that in June. And So that will allow us to basically, because safety is a huge issue with batteries in general, especially reused batteries, that CalC grant will pay for us to demonstrate this fire suppression system that doesn't damage any of the batteries, so we can deploy the fire suppression system if and when necessary, and then continue to use all the equipment without any issue. Yes?
Are you going to burn batteries?
Burn batteries? We did accidentally already, actually.
To test the system, the fire suppression system?
Yes. So, yeah, destructive testing will probably be necessary for that CalC grant. Yeah, we were testing some other manufacturers' BMS, and the BMS just didn't work, and so the batteries kept discharging and basically melted down in our lab a couple of years ago. So that is really part of what woke us up to the fact that existing battery management systems are unsafe and inefficient, for use, especially with these second life EV batteries. So that's when we went out and got our own and started working to kind of control our own destiny on that front.
Why deployment at a local business and not maybe like a larger manufacturer that can take a bit of wholesale, or does it give them larger savings by using your battery system, especially given the financial implications coming out with the lawsuit?
So this will be our first privately funded system, so it won't be dictated by grant funding. The goal is to gather up enough funding from various sources to make this happen, build a business case to demonstrate the economics of our system. By a local business, I mean it could be an industrial facility, in the Central Valley that has really spiky demand. Not many customers have what's called direct access to wholesale prices. That may or may not sort of serve the economics of this behind-the-meter energy storage that we're talking about. But we're open to all ideas on where to install this next system. It's not set in stone. And determining where to install this and what partners we want to execute that project with is really the primary goal of this National Science Foundation program this summer, which is directed at university startups like us to help us really hammer out our business model and partnerships and go-to-market strategy, et cetera. Any other questions? All right. I'll be here for a few more minutes. Thank you all for your time and attention.
Please sign in if you haven't. So we're directed by Brandon Payne, and if any people left, please take it with you as well.
We basically. The guts of their
Yes.
You just gotta think about like how much
Super neat.
yeah, I think
oh no, yeah. That is another aspect that makes that level
we haven't seen it.
gotta get a call on it. That's all.
I was like, I don't care the health. No, expected.
No, so I'm pretty brand new. I'm now the affiliate program no, so I'm yeah, so I'm EEI, so lighting, cooling, and water, and I handle all those trophy dealerships and get them onboarded as affiliates.
Because that's where you realize things.
Lots of opportunities to